We're going to turn now to the Graham-Schmidt process. So there's some terminology which I'm going to introduce right up front. There's something called an orthogonal basis of a vector space. There's also an orthonormal basis of a vector space, a related concept of an orthogonal matrix, and then the Graham-Schmidt procedure. Now, these first two words, orthogonal and orthonormal basis, those are actually pretty self-explanatory. A basis is said to be orthogonal if all of the vectors are orthogonal to each other. And a basis is said to be orthonormal if not only is it orthogonal, but each of the vectors has length 1. That is to say that vi dot vj, well, if I is not equal to j, it better be 0, so they're orthogonal, and if I is equal to j, they're supposed to be 1, so they're normal, or length 1. So that is to say, an orthonormal basis is one in which is orthogonal, and the vectors have length 1. Now, one thing I want to mention right at the beginning is if you have an orthogonal basis, v1 through vn, it's very easy to construct an orthonormal basis from it. So the picture is you have two, say, orthogonal vectors v1 and v2. Well, they're orthogonal. You don't know anything about their lengths, but you just scale each of them to make them length 1. And that's quite easy to do. So in some ways it's good to emphasize orthogonal bases and let the normal come along for the ride. So the basic point here is that if you have any vector at all, as long as it's not 0, if you just divide it by its length, that normalizes it. It makes it length 1. That is to say, the length of this new vector v prime is the length of v over the length of v, which is 1. So that is to say, if you're given an orthogonal basis, if you just replace each of the vectors with their normalized versions, that becomes... Okay, so a natural question is, how do you construct an orthonormal basis? Well, I actually don't think that's that great a question. I mean, how do you construct a basis at all? I don't really want to get into that. So I'm going to rephrase it as what I consider a better question. Suppose you're given a basis somehow, by hook or by crook. You have a basis v1 through vn. How do you modify it to make it orthonormal? In other words, given any basis, how do you convert it into an orthonormal basis? That's the question. And the answer is that's exactly what the Graham-Schmidt process does. So, well, that's not much of an answer yet until I explain how this works. So let's do that. So here's a picture. Suppose I have a basis of R2 with two fairly random vectors, v1 and v2. What's a natural way to get an orthonormal basis out of this? Well, the obvious thing is to first normalize the vector v1, just scale it to make it have length 1. So let's call that q1, and that's pictured here in red. Now, what about v2? Well, I need to find, if I'm going to make an orthonormal basis, I'd better find another vector which is perpendicular to q1. And the natural thing to do is to take v2 and add a multiple of q1 to it to make it perpendicular. So the picture is, here's the orthogonal complement to q1, and you have the vector v2, add some multiple of q1 to it to project it here onto the orthogonal complement. And that makes a new vector, v2 prime. That's mislabeled here. It should be v2 prime. And I've added a multiple of q1 in order to do that. So this is the key step. And then you just normalize it. So you take this v2 prime and you normalize it to make q2 prime. Excuse me, to make q2. And that's basically Graham-Schmidt. That's how it works. So let's summarize this. The general case, the general step, we have n vectors v1 through vn. What I'm going to do is I'm going to normalize v1 to make it q1. And then I'm going to take V2 and add some multiple of Q1 to it to make it perpendicular, and then normalize it to get Q2. And then we're going to take V3 and add some multiples of Q1 and Q2 to it, and then normalize it to get Q3, and so on. So finally, at the last step, I'm going to add some linear combination of the preceding Q's in order to make this thing orthonormal to them, and then normalize it, and that will give me Qn. So that in a nutshell is Gram-Schmidt, but how do you actually do it? Well, here's the key step. I'll go back to the picture I had before. Let's suppose we've found a single unit vector Q1, and I have some other arbitrary vector V2. How do I compute this projection in order to make it perpendicular to Q1? Well, let's see. This V2 prime is supposed to be V2 plus some constant times Q1. And you just have to tell me what this constant is. So the condition that it's supposed to satisfy is that this V2 prime is supposed to be perpendicular to Q1. So let's write that condition down. V2 prime dot Q1 is supposed to be 0. And that is to say V2 plus C Q1 dot Q1. And if you write that out, you get V2 dot Q1 plus C times Q1 dot Q1. And this is a unit vector, so that term is 1. So you simply get V2 dot Q1 plus C. Okay, and I asked you to make that 0. So let's see. I asked you to make V2 plus dot Q1 plus C equal to 0, which is to say C is equal to minus V2 dot Q1. So this new vector V2 prime is V2 minus this scalar V2 dot Q1 times Q1. And that's one step. You then have to normalize V2 prime, but that's the main step. So let's look at the general picture here, the general algorithm. So let's suppose that you found k of these normal vectors, and you're working on the k plus 1th vector. So you're looking at vk plus 1, and we're trying to get qk plus 1. Well, you first get vk plus 1 prime, which is vk, minus this multiple of q1, minus the similar multiple of q2, and so on, minus these multiples of each of the qk's, where each multiple is you take the vk plus 1 and dot it with the corresponding q. And then this vector will be orthogonal to all of the previous ones, and then you just normalize it, and that gives you qk plus 1. And you do that for n steps, and you're done. That's the Gram-Schmidt algorithm. Now, here's a variant of Gram-Schmidt, which I actually prefer. It's easier to calculate. When you normalize things, you get all these nasty square roots, which are really annoying. And so it's much better in some way to leave the normalization to the end. And here's how that works. You start with these vectors v1 through vn, and you define a new vector w1, which is just v1. And then w2 is v2 minus this multiple of w1. So it's just like what I did before with q1, except that I have to divide by this w1 dot w1. The denominator, there's a denominator in this formula. That's the only difference. And then you take w3 is v3 minus v3 dot w1 over w1 dot w1 times w1 minus v3 dot w2 over the length of w2 squared times w2, and so on. So what this does is it gives you a bunch of orthogonal vectors. The wi's are all orthogonal, and then at the very end you normalize them to get the qi's. And that saves you some trouble. Okay, so I'll do some examples of that in class. Let's go on and talk about something else. I'd like to talk about orthogonal matrices. And the way I'll explain this is, suppose you have n vectors v1 through vn, which are orthonormal. They're an orthonormal basis, and make them the rows of a matrix v1 through vn. That is to say, the rows of Q are orthonormal. Well, if that holds, then Q is said to be an orthogonal matrix. That is to say, by definition, a matrix is orthogonal if its rows are orthonormal. Now, the terminology is a little funny. You might want to call this an orthonormal matrix, but it's an orthogonal matrix, and I'll say something about that, why the terminology is such in a minute. So here's an example. Take this matrix. Take cosine theta, sine theta, minus sine theta, cosine theta. So the first row is the matrix cosine theta, sine theta, and cosine squared plus sine squared is equal to 1. And similarly the second row, so they're both normal, they're both length 1. And the orthogonality is if you take the dot product of cosine sine with minus sine cosine, you get 0. So this is an example of an orthogonal matrix. Okay, there's a very easy fact, and I recommend that you think of orthogonal matrices this way. A matrix is orthogonal if and only if Q times Q transpose is the identity. That's interesting. Why is that? Well, let's look at this example, or let's look at a 2x2 example. Suppose you have a 2x2 matrix and you ask if it's orthogonal. Well, if you look at this condition, QQ transpose, and you write it out, you get this, a squared plus b squared, ac plus bd, ac plus bd, and c squared plus d squared. And I'm asking, is that equal to the identity? That's the condition that I'm checking. And, well, it holds if a squared plus b squared and c squared plus d squared are both 1, which is to say the rows have length 1. And then AC plus BD equaling 0 says that they're orthogonal. And if you think about it, when you multiply Q times Q transpose, you're taking the dot products of all of the rows of Q with all of the other rows of Q. So that's why this is true. Now, let's look at this matrix with the cosines and sines again. This is a rotation matrix. It's rotation by angle theta. That is, if you take a vector v, it rotates it by angle theta. And such an action preserves angles. If you take two vectors at a given angle, it keeps the angle between them. And if you have a vector of a given length, it doesn't change it. So that's what I mean by a rigid motion. So that's actually a defining property of orthogonal matrices. So the theorem is that Q is orthogonal if and only if the following conditions hold. So first of all, we're going to require that it doesn't change dot products. The dot product of V and W is the same as the dot product of QV and QW for all vectors V and W. Now remember, V dot W is basically the cosine of the angle between them. And so this property is saying that this operation preserves angles. The second property, which is actually equivalent to the first, is that it preserves lengths. If you have a vector v, the length of qv and the length of v are the same. So this is a defining property of orthogonal matrices, and that's why they're called orthogonal, because they preserve angles and preserve lengths. Okay, so let's look at why this is true. Why is Q orthogonal if and only if this condition holds? Well, what does Q orthogonal mean again? It means that Q transpose Q is the identity. Well, I had said QQ transpose is the identity, but if you think about it, those two conditions are equivalent. So let's look at this one. So look at V dot W. Well, you can write that as V transpose times W. Well, what is QV dot QW? Well, that's QV transpose times QW. And remember, when you take the transpose, you change the order. So that's V transpose Q transpose times QW. And now regroup, you get the Q transpose Q in the middle. And of course, that's the identity. So it goes away and you get V transpose W, which is to say V dot W. So that basically explains why orthogonal is the same thing as preserving the dot product or preserving angles. And remember, the length of a vector is just the dot product with itself, or the square. And so if something preserves the dot product, it clearly also preserves lengths. All right, that's plenty for today. I'll see you in class.